This video is intended for informational purposes for MedImmune employees, our partners, and those interested in the accomplishments of a uniquely innovative and challenging project. The goal of the automation upgrade project at the Speak manufacturing facility was to completely redesign the egg-based bulk vaccine process from a series of manual steps to a fully automated system. Our team pushed the limits of technology without changing our manufacturing process. At the same time, we created a more sustainable, repeatable, and scalable platform to support an increased need for influenza vaccines. To enable MedImmune to successfully complete this project with the constraints that time, technology, and the egg-based bulk vaccine production process imposed on us, we needed to thoroughly plan how we would execute this project while thinking beyond the traditional pharmaceutical development and validation model. We had to innovate our project execution strategy prior to project inception. We could not simply start with a clean sheet of paper and design new systems. We needed to invent new manufacturing technologies out of state-of-the-art hardware and software and reinvent the traditional design, development, and validation models. By applying a strategy which reflects system engineering techniques, the overall bulk vaccine process was first broken down into the smallest logical subsystems: trolley, loader, unloader, candling, IPA spray, decap inspection, harvest, and inspection. We will use the trolley unloader as an example of how each of the subsystems was treated. In the existing process, trays were manually removed from trolleys one by one and moved to the processing areas. After the process, each tray was manually returned to the trolley. In total, every tray of eggs was manipulated by operators 7 times. This resulted not only in the potential of increased bioburden in the finished product, but also increased chances for damage to the eggs via drops, spills, and breakage. By applying a solution neutral statement, or SNS, to each of the subsystems, it allowed the team to develop different concepts of the subsystem without predisposition of a solution. For this project, only one overarching SNS was necessary. The solution neutral statement was making the current vaccine manufacturing process to a scalable, repeatable, and sustainable system which will perform to the identified regulatory requirements for live attenuated influenza vaccine intranasal. Once the SNS was applied to each subsystem, the team thoroughly researched and investigated numerous conceptual designs for each of the subsystems that would meet the acceptance criteria. The concepts for each were then narrowed to what was considered the best solution for that subsystem. The solution was designed via CAD or solid modeling software and then prototype tested. One of the ways this project was unique was the strategy to integrate the SMEs and the suppliers from concept to FAT. By forming the SME and the suppliers into one team, they were able to quickly advance and accommodate increasing levels of fully integrated automation. Our process can be mathematically modeled using the following equation. A classic control system feedback network was used to continually update the model and the actual subsystem to integrate the iterations in interfaces as new features and automation strategies were developed in other subsystems. This can be represented mathematically with F sub I defined as the interfaces with different subsystems. This process could require several iterations. The output of this was the final subsystem. Shown here, a trolley unloader is installed at the beginning of each automation line. Each trolley holds 120 trays for a total of over 4,000 eggs. The trolley unloader automatically delivers the trays to the downstream equipment without manual handling. Operators guide a full trolley into the system. After the trolley is in place, they close the doors around the trolley and lower the safety bar to enable operation. Once initiated, the unloader sends the elevator to the individual levels of the trolley and guides the trays onto the spoons. After they are secured on the spoons, the elevator lowers to the conveyor height and guides the trays onto the conveyor where they are sent for further processing. This process is repeated for each level until the trolley is empty. We shall now describe how each of the subsystems work both in the old configuration and then in the new. First, the candling system. In the previous process, eggs were candled in a darkened room where trays of eggs were manually removed from trolleys by operators and placed on special tables for inspection by trained personnel. The eggs were visually inspected via candling, and eggs which were damaged, infertile, or otherwise unsuitable were discarded. The remaining eggs were then sent on to further processing. The initial design yielded this solid model. And now, the new candling system. As the candler analyzes the eggs, it presents its findings on the HMI, where a trained operator is stationed. When the analysis is complete, it presents the questionable eggs to the operator for their confirmation of suitability. The operator selects to view an enlarged image and determines that it is acceptable for further processing. The selection is verified, and the process continues to the next tray. After candling, the trays are entered into the egg removal section of the candler. Here, vacuum cups lower over the tray, and individual eggs which have been rejected are picked up and placed on a belt where an operator removes them for disposal to waste. During this process, the vacuum cups touch only the eggs which are being rejected and do not make contact with those which will be sent for further processing. For the IPA spray process, in the previous process, isopropyl alcohol, or IPA, was manually sprayed by operators over each tray of eggs prior to harvest. This resulted in increased operator exposure to IPA and inconsistent and uneven distribution of IPA from tray to tray and from operator to operator. For the new IPA spray process, trays of eggs are automatically fed to the IPA spray station from the trolley unloading system. The IPA spray is triggered and evenly distributes IPA to the tops of the eggs to prepare them for decapping. Following a short pause to allow for drying, the tray is moved on for further processing and the next tray enters the station. And now for the decapping step. In the previous process, a team of operators manually decapped each egg by egg and tray by tray, using a handheld pneumatic popper. Once cut, the operator manually removed the individual caps using a scalpel and pushed the embryo aside with a spatula to enable harvesting. The operator then performed a subjective assessment of suitability for harvest. This step required the operator to physically handle each and every egg. 36 eggs took 15 minutes, and introduced the risk of bioburden to each egg. The results of manual inspection were subjective and therefore not scientifically repeatable. With the new decapping system, the tray of eggs is conveyed to the decap station, where the eggs are lifted from the tray to expose the tops above the dead plate. The blade quickly cuts through the tops of the eggs, exposing the allantoic fluid. A combination of pressurized air and vacuum pulls the caps away from the station and into a waste container. The tray leaves the decap station prior to retracting the blade and continues down the conveyor for decap inspection. With the new inspection system, a vision system scans and analyzes the tray of decapped eggs. The system determines which eggs are acceptable, which are unacceptable, and notifies the operator of any questionable eggs. Eggs which have been rejected will not be harvested. The trained operator confirms their selection for further processing and awaits the next tray. Between inspections, the operator switches screens on the HMI and checks the status of the overall harvesting system. From this HMI, the health of the entire harvesting operation can be monitored. In the existing harvest process, the operator visually inspected the fluid as it was drawn into the pipette. If it was subjectively deemed by the operator to be acceptable, it was pulled into an aliquot. If it was determined to be unacceptable, it was dispensed to waste and the pipette was disposed of. Eggs which have been harvested exit the harvest station, and any nozzles which have aspirated rejected fluid are flushed prior to the next tray of eggs entering the harvest station. The next tray enters and nozzles are lowered into the eggs which have been accepted by the decap inspection station. The fluid from these eggs is aspirated to the syringes of the fluid inspection station. This is the fluid inspection station. Accepted decapped eggs are aspirated to individual inspection syringes. Immediately following aspiration, the vision system scans the fluid and determines if it should be accepted or rejected. Here, all fluid is deemed acceptable and is sent to the aliquot where it will be further processed. A trained operator stationed at the Harvest Inspection HMI is presented with images of questionable harvested fluid. The operator reviews the images to determine if the fluid should be accepted or rejected. The choices are confirmed, and the system continues to the next tray of eggs. The process is repeated as each tray is harvested. There are 9 harvest nozzles per fluid inspection station and 36 harvest nozzles in total on the system. The fluid inspection station scans and analyzes all 36 syringes in less than 2 seconds. The team devised a creative and flexible solution to the problem. We designed and built a temporary manufacturing building, or TMB, at the UK1 manufacturing site to co-locate the new systems with the current manufacturing team. The resolution was to use this building to perform equipment and process development and to optimize processing parameters. By utilizing the TMB, cross-functional teams including manufacturing, maintenance, quality assurance, and quality control personnel were exposed to the new systems and equipment early, near home, and gained valuable operating experience. The TMB was designed to fully replicate the commercial manufacturing process. This design included all support systems such as primary incubators, secondary incubators, and chillers. The design team used the TMB to supply daily batches of eggs for system debugging and optimization, operator training, and process documentation development. Over 90 development batches were performed in the TMB during the project, in parallel with commercial manufacturing, replicating the challenge of a manufacturing season without a single loss of commercial product. The result of our innovative approach was a new, integrated, automated process stream providing 7 efficiency improvements. First, an increase in our per egg harvest yield from 6.3 to 6.8 ml per egg during training batches to 8.7 ml per egg during production runs. Second, a reduction in egg manual handling events from 8,970 to 4 in candling, incubation, and harvesting. Third, a reduction in incidence of rejection of high bioburden harvest fluid by 8%, increasing the harvest pass rate from 81.1% to 89.1%. Fourth, non-viable egg candling accuracy to within 0.2% accuracy to manual methods, and detection of 100% of non-viable eggs. Fifth, reduction in operator decisions in process from 100% to 10%. Sixth, increased candling throughput from 2,500 eggs per hour to 10,000 eggs per hour. And seventh, a reduction in seasonal headcount of 25%. In completely redesigning the egg-based bulk vaccine process from a series of manual steps to a fully automated system, our team pushed the limits of state-of-the-art and advanced technology without changing the manufacturing process. By using techniques similar to systems engineering and our overarching solution neutral statement, SNS, our innovative approach produced a new, integrated, automated process stream, creating a more sustainable, repeatable, and scalable SRS platform, which will be able to meet increased demands. Sustainable, primed for operational excellence and continuous improvement. Repeatable, replaced all subjective inspections with automated, objective inspection systems. And scalable, can deploy more automation systems to respond to any increase in demand. We created a state-of-the-art vaccine manufacturing facility that is poised to respond to any influenza pandemic, with the capability of expanding our production 500% while maintaining process control and product quality. This process has the capability of analyzing and harvesting 7,500 eggs per hour. The UK LAIV Automation Upgrade Project developed innovative project execution strategies which enabled a creative and collaborative environment which ultimately advanced the biopharmaceutical industry and resulted in over 20 industry-first innovations. We hope you enjoyed this informational video as much as we, the UK Automation Upgrade team, enjoyed the project.